Electrochemistry. Electric transport. A substance which allows an electric current to pass through it is called a conductor, while the substance which does not allow electric current to flow through it is called an insulator or non-conductor. The conductors are of two types, which electronic conductors and electrolytic conductors. First is electronic conductors are the substances which do not undergo any chemical change as the electric current flows through them. For example, metal, graphite, and some minerals. The conduction through electronic conductors is due to the flow of electron in them. Electrolytic conductors are those conductors in which conduct electricity in their molten state or through their aqueous solution and which are decomposed by the passage of electric current. For example, aqueous solution of acid, base, and salt, molten salts. In this type of conductors, the electric current is due to the movement of by ions. This type of conduction is referred to as electrolytic conduction. Electrolytes are further classified as strong electrolytes and weak electrolytes. Strong electrolytes. Strong electrolytes are substances which are almost completely dissociated into ions in the aqueous solution or in the molten state. For example, strong acids like HCl, H2SO4, etc. Strong bases like NaOH, KOH, etc. and salts like NaCl, NH4Cl, etc. Weak electrolytes are substances which dissociate in aqueous solution to a smaller extent. In other words, they have low degree of dissociation. For example, weak acids like HCN, H3PO4, CH3COH, and weak bases like NH4OH, etc. Since they have low degree of dissociation, so they conduct electricity to a small extent. Non-electrolytes, substances like urea, glucose, etc. which do not conduct electricity in molten state or through their aqueous solutions are called non-electrolytes. Ethyl alcohol, sugar are also examples of non-electrolytes. It is interesting to note that whereas the electrical conduction of electronic conductors decrease with increase of temperature, but in case of electrolytic conductors it increases with temperature. Factors affecting electrolytic conduction. In aqueous solution or molten state, the electrolytes split up into ions. The free movement of ions is responsible for the conduction of electricity. The electrical conductivity of solution should therefore be related to the number of ions present in the solution. Some of factors on which electrical conductivity of the solution of electrolytes depends are: first is the interionic attraction. These are the attractive interactions between the ions formed by the electrolytes in solution and are known as solute-solute interaction. Large the interionic attraction, lesser is the freedom of movement of ions and smaller will be the electrical conductivity. The solvation of ions. These are the attractive interactions between the ions of the electrolyte and molecules of the solvent and are known as solute-solvent interactions. Larger the solute-solvent interactions, larger will be the solvation, lesser will be the movement of ions and hence lower will be the electrical conductivity. Viscosity of solvent. The factor depends upon the attractive interaction between the solvent molecule, which is referred to as solvent-solvent interaction. Larger the solvent interaction, which is referred to as solvent-solvent interaction, larger the movement of ion, hence lower will be the electrical conductivity. The above factor decrease with increase in temperature. As a result, the kinetic energy of the ions increase on increase in temperature. This results in the increase of electrical conductance of electrolytic solution with rise in temperature. This is in contrast to the behavior of electronic conductors in which the conductance decreases with increase in temperature. Alternatively, we can say that conductivity of electrolytic solutions depends upon the following factors. First is nature of electrolyte. The conductance of an electrolyte depends upon the number of ions present in the solution. The number of ions produced by an electrolyte ions in solution and therefore their solutions have high conductance whereas weak electrolyte dissociate to only small extent, hence Their solutions have low conductance. Nature of solvent. Electrolytes ionize to greater extent in polar solvents, therefore greater the polarity of the solvent. Larger is the ionization and hence greater is the conductance. Concentration of solution. On increasing the concentration of electrolytic conductance, decreases in case of both weak as well strong electrolytes, because with increase in concentration in case of weak electrolytes, the ionization decreases, and in case of strong electrolytes, the interionic attraction increases. Temperature. The conductivity of an electrolyte depends upon the temperature. With increase in the temperature, the conductivity of an electrolyte increases due to increase in dissociation. The difference between metallic conductors and electrolytic conduction are given in table 1. Difference between metallic conductor and electrolytic conductor. Electrical resistance and conductance. Electrolyte solutions conduct electricity through them by the movement of ions towards the electrodes. Like metallic conductors, electrolytic conductors also offer resistance to the flow of electricity. Hence, electrolytes also obey Ohm's law. According to Ohm's law, the current I flowing through a metallic conductor is directly proportional to the potential difference across it. I directly proportional to V. I equals to V divided by R. V equals to IR, where R is the constant of proportionality and is known as resistance of the conductor. It is expressed in ohms and is represented by this. Current is generally measured in amperes and potential difference V is measured in volts. According to Ohm's law, R into ohms is equal to V into volts divided by I in amperes. Units of resistance. Unit of resistance is ohm in terms of SI base unit equals to kg meter square divided by S cube A square. The interesting feature of electrolytic solution is not the resistance they offer to the flow of electricity, but they allow it to flow. Consequently, the important property in electrochemistry is conductance. Thus, conductance is a measure of SA with which current flow through a conductor. From Ohm's law, it follows that a substance which offers lesser resistance will allow more electricity to pass through it. Thus, conductance is the reciprocal of resistance. It is represented by C. C equals to 1 by R. Unit of conductance are reciprocal of ohm, like ohm inverse or mho. Electrical conductance is also expressed in Siemens, named after noted electrical engineer Sir William Siemens. Specific conductance, equivalent conductance, and molar conductance. Specific conductance. The resistance R of conductor is directly proportional to its length and inversely proportional to its area of cross section. R is inversely proportional to L by A, or R equals to rho into L by A, where rho is the constant of proportionality and is known as specific resistance or resistivity. Value of rho depends upon the material of the conductor. From equation 1 we have rho equals to R. Thus, the specific resistance or resistivity rho is defined as the resistance of a conductor of 1 cm length and having area of cross section equal to 1 cm square. In other words, resistivity or specific resistance is the resistance between opposite faces of an centimeter cube of a conductor. In SI units, it is defined as resistance when the conductor is 1 meter long and its area of cross section is 1 meter square. Resistance of a 1 meter cube of the conductor. Units of resistivity are ohm centimeters. SI unit are ohm meter. The reciprocal of specific resistance rho is known as specific conductance. It is denoted by the symbol kappa. Thus, kappa equals to C multiply L by A, when L equals to 1 and A equals to 1, kappa equals to C of volume 1 centimeter cube. The conductance of each of these cubes is equal to specific conductance. Thus, the total conductance of the solution will be 4 multiply kappa. Similarly, VCC of solution will form V cubes and the total conductance will be kappa multiply V. In general, for a solution containing 1 gram equivalent of electrolyte in V centimeter cube, we have equivalent conductance is equal to specific conductance multiply V. In terms of concentration of a solution contains C gram equivalent of electrolyte in 1000 gram CCC. The solution then the volume of solution containing 1 gram equivalent will be 1000 divided by C. Thus expression 1 can be written as del EQ equals to kappa multiply 1000 divided by normality. Units of equivalent conductance. The SI unit are S meter square EQ minus 1. Molar conductance. Molar conductance of a solution at a dilution V is defined as the conductance of all the ion produced from 1 mole of electrolyte dissolved in VCC of solution such that the whole of the solution is placed between two parallel electrodes 1 centimeter apart. It is denoted by del m. Relation between molar conductance and specific conductance. Molar conductance of solution is obtained by multiplying the specific conductance by the volume in Cc, which contains 1 mole of the electrolyte. Thus, del m equals to kappa K into V, where K is the volume of solution in centimeter cube containing 1 gram mole of the electrolyte. If a solution contains C moles of electrolyte in 1000 CCC of the solution, then the volume of the solution containing 1 mole will be 1000 divided by C. Thus, above expression can be written as del m equals to K multiply volume in centimeter cube containing 1 mole of electrolyte. Del m equals to kappa multiply 1000 divided by C or equals to kappa multiply 1000 divided by molarity. Here kappa is the specific conductance and C is the molar conductance. Unit of molar conductance is ohm inverse centimeter square mole inverse. According to SI system, in SI units, when K is in S meter inverse and molarity is in mole meter minus 3 cube, then del m has units S meter square mole inverse. Both the types of units are related to each other as measurement of conductance, specific conductance, equivalent conductance and molar conductance. Measurement of conductance. The conductance of solution is reciprocal of resistance. Therefore, it can be determined by measurement of resistance of solution. The resistance of a solution can be measured with the help of Wheatstone bridge method. The principle of Wheatstone bridge method is as follows. It consists of 4 resistance R1, R2, R3 and R4. Resistance R1 is a variable resistance and R2 is known resistance of the electrolyte solution. When the current flows resistance of the electrolyte solution, when the current flows through the circuit, the resistances R1, R2, R3 are so adjusted that a null point is obtained. The null point is inducted by zero deflection in the galvanometer G. At null point, R1 divided by R2 equals to R3 divided by R4. The resistances R1, R3, R4 are known as the value of R2 can be calculated. To determine the resistance of the electrolyte solution, one arm of Wheatstone bridge is attached to the conductivity cell containing the solution. The conductivity cell is made of Pyrex glass and is fitted with platinum electrodes. These are coated black with finely divided platinum. However, for measuring the resistance of an electrolyte solution, direct current DC cannot be used because it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrode changes and this results in the change in the resistance of the solution. These effects are called polarization effects. To overcome this problem, following modifications are done in the usual Wheatstone bridge method. The bridge is connected to a source of alternative current at frequency of 550 to 5000 cycles per second is employed. A headphone is used in place of galvanometer because with alternating current or ordinary galvanometer fails to detect the null point. The cell is placed in a thermostat to keep the temperature constant. This is to avoid changes in conductance with temperature. Electrodes are coated with platinum black. The arrangement used for measurement of resistance is shown in figure 5. A shielding contact J moves over a stressed wire ABR is the resistance box and conductance cell containing electrolyte solution is placed in the circuit. There is a source of alternating current in resistance R is introduced in the resistance box. The sliding contact J is moved along the wire AB until the sound in the earphone is minimum, say at point H. If X is the resistance of the electrolyte solution, then according to Wheatstone bridge principle, we have resistance R divided by resistance X equal to resistance AH divided by resistance BH equals to length AH divided by length BH. Resistance X equals to resistance R multiply length AH divided by length BH. From the values of R and length AH and BH obtained from null point, we can calculate the resistance X of the electrolyte solution can be calculated. The resistance of electrolyte solution is converted to conductance using the following equation. Conductance C equals to 1 by X equals to 1 by R multiply length BH divided by length AH. Calculation of specific conductance. The specific conductance kappa of electrolyte solution can be calculated as follows. Kappa equals to C multiply L by A, where C is the conductance of solution. Here L is the distance of separation of two electrodes and A is area of cross section of electrodes. The quantity L by A is cell constant. The cell constant is expressed in the units electrodes. The cell constant is expressed in the units centimeter inverse. The equation 1 can be written as specific conductance kappa equals to conductance multiply cell constant. Once the specific conductance is determined, the equivalent conductance del EQ and the molar conductance del M of solution can be calculated. We have the expression specific conductance K equals to 1 by R multiply L by A. Specific conductance equals to observed conductance multiply cell constant. Determination of cell constant. The cell constant L by A can be determined by measuring the distance L between the electrodes of a cell and their area of cross section. Actual measurement of these dimensions for a given cell is difficult. Therefore, an indirect method is used to determine the value of cell constant of a cell. The cell constant is generally not calculated from the values of L and A because these are difficult to measure for a cell. However, it is usually determined accurately by measuring the conductance of a standard solution of KCl, whose conductivity is known at different concentration and temperatures. The conductivity of different KCl solution at 298 Kelvin are given in table 2. Once the cell constant is known, the specific conductivity of the given solution can be calculated from the observed conductance of the solution. For example, for 0.1 m KCl solution at 298 Kelvin, conductivity is 0.0129 s centimeter inverse. Suppose the conductance of the solution in the given cell is measured to be x, then cell constant equal to conductivity divided by conductance equals to 0.0129 divided by x. Fourth is calculation of equivalent conductance del EQ. Del EQ equals to kappa multiply 1000 divided by CEQ, where CEQ is the concentration in gram equivalents per liter. That is the molar normality of the solution. Thus, knowing specific conductance and normality of solution, we calculate equivalent conductance of the solution. Calculation of molar conductance del M. Del M equals to kappa multiply 1000 divided by Cm, where Cm is the concentration in mole per liter, that is the molarity. Thus, knowing the value of molarity and specific conductance, we can calculate molar conductance of the solution. Units of common terms used in conductance are summed up below. Sixth is activity of water. For accurate conductance measurements, the solution are prepared in extra pure water, which is free from dissolved impurities. The extra pure water has very small conductance, such as extra pure water is called conductivity water. The specific conductance of this water is as low as 4.3 multiply 10 raised to power minus 8 s centimeter inverse. For practical purposes, conductivity water can be prepared by distilling ordinary water containing a small quantity of potassium permanganate, only a few crystals, and sodium hydroxide twice in a Pyrex glass distillation apparatus. Variation of conductance, specific conductance, equivalent and molar conductance with dilution. Generally, the electrolytic conduction decreases with increase in concentration or increases with increase in dilution. Thus, this is because the conductance is due to presence of ions in the solution. The greater the number of ions, the greater is the conductance. With dilution, more ions are produced in a solution, so conductance also increases on dilution. The specific conductance is the conductance of 1 centimeter cube of solution. On dilution, the specific conductance decreases because the concentration of ions per centimeter cube decreases and therefore the specific conductivity decreases. On the other hand, the molar conductivity and equivalent conductivity increase on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance, and the volume V of the solution containing 1 mole or 1 gram equivalent of the electrolyte del equals to kappa multiply V. On dilution, the specific conductance decreases, but the increase in volume is much more than decrease in specific conductance. As a result, molar conductance and equivalent conductance increase with dilution. Variation of molar conductance with dilution or for strong and weak electrolytes. The variation of molar conductivity on dilution for strong and weak electrolytes can be studied by plotting del M values against root C. The variation of del M with concentration is discussed below. For a strong electrolyte, the molar conductance of strong electrolytes in dilution solution varies with concentration according to the Debye-Huckel-Onsager equation as follow: del M equals to del M infinity minus B root C, where del M is the molar conductance at concentration C and del M infinity is the molar conductance at infinite dilution and is called limiting molar conductance. Here B is a constant which depends upon the type of electrolyte, nature of solvent and temperature. It is found that for strong electrolytes, example KCl and Debye-Huckel-Onsager equation holds good at low concentration. As a result, the variation of del M is linear at low concentration, figure 7, but it does not remain linear for higher concentration. The curve for strong electrolytes shows that there is a small increase in molar conductance with dilution. This explained as follows: strong electrolytes are completely dissociated at all concentration. Thus, the number of the current carrying species, i.e. the ions, remains constant on dilution. Hence, the increase in molar conductance is not due to the increase in number of ions. It is due to the fact that at higher concentration, the intra-ionic attraction, i.e. that is the forces of attraction between the oppositely charged ions, are appreciable. This retards the motion of ions, therefore the molar conductance falls with increase in concentration. On the other hand, with decrease in concentration, the ions are far apart and the forces of attraction between them decreases, due to which the molar conductance increases with dilution as the solution becomes more and more dilute. The molar conductance increases till it reaches a maximum limiting value. This value is known as molar conductance at infinite dilution and is denoted by del M infinity or del M naught. The value of del M naught can be obtained by extrapolating the curve to a value of root C equals to 0. Second, for a weak electrolyte, the weak electrolyte are dissociated to a lesser extent as compared to strong electrolytes. Hence, the molar conductance of a weak electrolyte is much less than that of strong electrolyte at the same concentration. Figure 7 shows that the molar conductance of acetic acid is lesser than that of KCl. At the same concentration, the curve shows that for a weak electrolyte there is a large increase in molar conductance with dilation, especially near infinite dilution. The increase in molar conductance with dilution is due to the increase in the number of ions. Thus, the increase in molar conductance with dilution in case of weak electrolytes is due to increase in the degree of ionization of the electrolyte on dilution. However, there is no indication of limiting value of del M naught even when the concentration approaches 0. From figure 7, it is observed that the curve for a strong electrolyte becomes linear at low concentrations and hence it can be extrapolated to zero concentration. To obtain the value of molar conductance at infinite dilution, as del m naught, but for a weak electrolyte, the limiting value of molar conductance del m naught cannot be obtained by extrapolation. There is an indirect method for obtaining molar conductance at infinite dilution for weak electrolytes, which is based on Coulomb's law. Next is Arrhenius' theory of ionization. Arrhenius stated the conductance of aqueous solution of different electrolytes. He proposed that the conductance of solution was due to the presence of ions. Arrhenius put forward his theory of ionization in 1884. Arrhenius' theory of ionization is summarized as follows. An electrolyte, when dissolved in water, splits up into charged particles called ions. The positively charged particles are called cation and the negatively charged particles are called anions. In the modern view, the theory assumes that the electrolytes are already ionized in the solid state and these ions are held by electrostatic forces. When the electrolyte is dissolved in water, the electrolyte dissociation to form separate cations and anions. Thus, AB for the region. This theory is called as theory of electrolytic dissociation. Second is the charge carried by cations is equal to the charge carried by anions. As a result, the electrolytic solution is electrically neutral. The charged ions move through the solution towards the oppositely charged electrode. This migration of ions causes the passage electric current through the electrolyte solutions. This explains the conductance of electrolytes and the phenomena of electrolysis. The electrolyte may not be completely ionized. The ratio of dissociated molecules to the total number of molecules is called degree of dissociation, denoted by alpha. Thus, degree of dissociation alpha equals to number of molecules dissociated divided by total number of molecules. Next is the ions formed in the solution constantly reunite to form undissociated molecules. Thus, a state of equilibrium exists between the undissociated molecule and the ions formed by the dissociation of electrolyte. The equilibrium constant for this equilibrium constant for this equilibrium is written as K equals to A plus B minus divided by concentration of AB, where K is called the dissociation constant. Sixth is the degree of dissociation increase on dilution and become maximum at infinite dilution. Seventh is the electrical conductance of an electrolyte solution depends upon the number of ions present in solution. So greater the degree of dissociation, higher is the conductance. Thus, the degree of dissociation of an electrolyte determines whether it is strong electrolyte or a weak electrolyte. Mineral acids and salts have high conductance values. Activity of water. For accurate conductance measurements, the solution are prepared in extra pure water, which is free from dissolved impurities. The extra pure water has very small conductance, such as extra pure water is called conductivity water. The specific conductance of this water is as low as 4.3 multiplied 10 raised to power minus 8 as centimeter inverse. For practical purposes, conductivity water can be prepared by distilling ordinary water containing a small quantity of potassium permanganate, only a few crystals, and sodium hydroxide twice in a Pyrex glass distillation apparatus. Variation of conductance, specific conductance, equivalent and molar conductance with dilution. Generally, the electrolytic conduction decreases with increase in concentration or increases with increase in dilution. Thus, this is because the conductance is due to presence of ions in the solution. The greater the number of ions, the greater is the conductance. With dilution, more ions are produced in a solution, so conductance also increases on dilution. The specific conductance is the conductance of 1 centimeter cube of solution. On dilution, the specific conductance decreases because the concentration of ions per centimeter cube decreases and therefore the specific conductivity decreases. On the other hand, the molar conductivity and equivalent conductivity increase on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance, and the volume V of the solution containing 1 mole or 1 gram equivalent of the electrolyte, del equals to kappa multiply V. On dilution, the specific conductance decreases, but the increase in volume is much more than decrease in specific conductance. As a result, molar conductance and equivalent conductance increase with dilution. Variation of molar conductance with dilution or for strong and weak electrolytes. The variation of molar conductivity on dilution for strong and weak electrolytes can be studied by plotting del M values against root C. The variation of del M with concentration is discussed below. For a strong electrolyte, the molar conductance of strong electrolytes in dilution solution varies with concentration according to the Debye-Huckel-Onsager equation as follow: del M equals to del M infinity minus B root C, where del M is the molar conductance at concentration C and del M infinity is the molar conductance at infinite dilution and is called limiting molar conductance. Here B is a constant which depends upon the type of electrolyte, nature of solvent and temperature. It is found that for strong electrolytes, example KCl and Debye-Huckel-Onsager equation holds good at low concentration. As a result, the variation of del M is linear at low concentration, figure 7, but it does not remain linear for higher concentration. The curve for strong electrolytes shows that there is a small increase in molar conductance with dilution. This explained as follows: strong electrolytes are completely dissociated at all concentration. Thus, the number of the current carrying species, i.e. the ions, remains constant on dilution. Hence, the increase in molar conductance is not due to the increase in number of ions. It is due to the fact that at higher concentration, the intra-ionic attraction, i.e. that is the forces of attraction between the oppositely charged ions, are appreciable. This retards the motion of ions. Therefore, the molar conductance falls with increase in concentration. On the other hand, with decrease in concentration, the ions are far apart and the forces of attraction between them decreases, due to which the molar conductance increases with dilution as the solution becomes more and more dilute. The molar conductance increases till it reaches a maximum limiting value. This value is known as molar conductance at infinite dilution and is denoted by del M infinity or del M naught. The value of del M naught can be obtained by extrapolating the curve to a value of root C equals to 0. Second, for a weak electrolyte, the weak electrolyte are dissociated to a lesser extent as compared to strong electrolytes. Hence, the molar conductance of a weak electrolyte is much less than that of strong electrolyte at the same concentration. Figure 7 shows that the molar conductance of acetic acid is lesser than that of KCl. At the same concentration, the curve shows that for a weak electrolyte there is a large increase in molar conductance with dilution, especially near infinite dilution. The increase in molar conductance with dilution is due to the increase in the number of ions. Thus, the increase in molar conductance with dilution in case of weak electrolytes is due to increase in the degree of ionization of the electrolyte on dilution. However, there is no indication of limiting value of del M naught even when the concentration approaches 0. From figure 7, it is observed that the curve for a strong electrolyte becomes linear at low concentrations and hence it can be extrapolated to 0 concentration. To obtain the value of molar conductance at infinite dilution as del M naught, but for a weak electrolyte, the limiting value of molar conductance del M naught cannot be obtained by extrapolation. There is an indirect method for obtaining molar conductance at infinite dilution for weak electrolytes, which is based on Coulomb's law. Next is Arrhenius' theory of ionization. Arrhenius stated the conductance of aqueous solution of different electrolytes. He proposed that the conductance of solution was due to the presence of ions. Arrhenius put forward his theory of ionization in 1884. Arrhenius' theory of ionization is summarized as follows. An electrolyte, when dissolved in water, splits up into charged particles called ions. The positively charged particles are called cation and the negatively charged particles are called anions. In the modern view, the theory assumes that the electrolytes are already ionized in the solid state and these ions are held by electrostatic forces. When the electrolyte is dissolved in water, the electrolyte dissociation to form separate cations and anions. Thus, AB for the region. This theory is called as theory of electrolytic dissociation. Second is the charge carried by cations is equal to the charge carried by anions. As a result, the electrolytic solution is electrically neutral. The charged ions move through the solution towards the oppositely charged electrode. This migration of ions causes the passage electric current through the electrolyte solutions. This explains the conductance of electrolytes and the phenomena of electrolysis. The electrolyte may not be completely ionized. The ratio of dissociated molecules to the total number of molecules is called degree of dissociation, denoted by alpha. Thus, degree of dissociation alpha equals to number of molecules dissociated divided by total number of molecules. Next is the ions formed in the solution constantly reunite to form undissociated molecules. Thus, a state of equilibrium exists between the undissociated molecule and the ions formed by the dissociation of electrolyte. The equilibrium constant for this equilibrium is written as K equals to A plus B minus divided by concentration of AB, where K is called the dissociation constant. Sixth is the degree of dissociation increase on dilution and become maximum at infinite dilution. Seventh is the electrical conductance of an electrolyte solution depends upon the number of ions present in solution. So greater the degree of dissociation, higher is the conductance. Thus, the degree of dissociation of an electrolyte determines whether it is strong electrolyte or a weak electrolyte. Neutral acids, alkalis, and salts have high conductance values because they are almost completely dissociated in the aqueous solution. These substances are termed as strong electrolytes, whereas organic acids, some inorganic acids like H2CO3, S3PO4, and bases like NH4OH, etc., have poor conductance because they have low degree of dissociation. Such substances are termed as weak electrolytes. Factors affecting the degree of dissociation. The degree of dissociation of an electrolyte depends upon the following factors: nature of solute, nature of solvent, concentration, presence of common ions, temperature. The degree of dissociation increases with rise in temperature. Ostwald dilution law, ionization of weak electrolytes. It has been mentioned earlier that weak electrolytes are ionized only partially. According to Arrhenius' theory of ionization, the ions formed as results of dissociation of weak electrolytes are present in dynamic equilibrium with the undissociated molecules. Consider the ionization of a binary weak electrolyte. In 1988, Ostwald applied law of chemical equilibrium to such chemical equilibria and obtained a relationship called Ostwald dilution law. Let C moles per liter be the concentration of electrolyte in the solution and alpha be its degree of dissociation. The concentration of various species at equilibrium would be H under. Applying law of chemical equilibrium, K of D equals to C alpha square divided by 1 minus alpha. When Kd is the dissociation constant of an electrolyte AB, like any other equilibrium constant, Kd is constant only at constant temperature. For weak electrolytes at ordinary concentration, 1 is greater than alpha. Therefore, alpha can be neglected in comparison to 1 in the denominator of expression 1. Then the simplified formula becomes Kd equals to C alpha square. Alpha square equals to Kd by C. Alpha equal to under the root Kd by C. Expression 1 and 2 are the forms of Ostwald dilution law. Expression 2 can be expressed as alpha directly proportional to under the root 1 by C. From equation 2, it is obvious that the degree of dissociation alpha increases as C decreases. As C approaches 0, alpha approaches 1. Thus, Ostwald's dilution law may be stated as for a weak binary electrolyte, the degree of dissociation is inversely proportional to the square root of the molar concentration. Further, as C is the concentration in moles per liter, then the volume of solution containing 1 mole of electrolyte will be 1 by C liters. Equation 1 and 2 can be written as alpha equals to under the root Kd into V, where V is the volume of solution in liter containing 1 mole of solute. Thus, Oswald's dilution law may also be stated as for a weak binary electrolyte, the degree of dissociation is directly proportional to the square root of the volume in liters containing 1 mole of the electrolyte. Validity of Ostwald's dilution law. The test the reliability of Ostwald's dilution law. The degree of dissociation alpha is determined from conductance measurements at various concentrations for different electrolytes. The values of alpha are obtained experimentally using the following expression. Alpha equals to del C divided by del naught, where del C and del naught are the equivalent conductances at concentration C and infinite dilution respectively. These values are determined from conductance experiments using Coulthard's law. The value of alpha are then substituted in the expression Kd equals to alpha square divided by 1 minus alpha into V. If the values of Kd are found to be constant, the Ostwald's law is verified. Limitations of Ostwald dilution law. Its limitations are explained as follows. Ostwald's dilution law holds good only for weak electrolytes in dilution solutions and fails completely in case of strong electrolytes like HCl, NaOH, and salts etc. Ostwald's law is based on Arrhenius theory of dissociation, according to which only a fraction of electrolyte dissociate at ordinary concentrations and complete dissociation occur only at infinite dilution. This is true only for weak electrolytes, as strong electrolytes are almost completely dissociated at all concentrations, and hence the formula del C divided del naught does not give correct value of alpha. Third is the derivation of Ostwald's law is based on law of mass action, which is not applicable to the ionic equilibria where the concentration of ions is high. Thus, the law of mass action in its simple form does not hold for equilibria involving strong electrolytes. As a result, the correct value of alpha is not obtained. Hence, Ostwald's law is not obeyed in case of strong electrolytes. Explanation for failure of Ostwald's dilution law. The failure of Ostwald's dilution law in case of strong electrolytes has been satisfactorily explained by Debye and Haeckel in 1923 and Onsager in 1927. According to them, these four must obey. First is strong electrolytes are almost completely dissociated at all concentrations. The ratio of del C divided by del naught does not represent the degree of dissociation alpha of strong electrolytes but is only a conductivity ratio. For a strong electrolytes, alpha equal to del C divided by del naught does not hold because when alpha equals to 1, alpha C is not equal to del C divided by del naught. In case of strong electrolytes, the increase in del C with dilution is not due to the increase in the degree of dissociation but due to an increase in the mobility of the ions of strong electrolytes. The lower value of del C as compared to the value of del naught is due to the decrease in the mobility of ions arising from relaxation and electrophoretic effects. However, at infinite dilution, these two retarding effects disappear. Hence, the value of del C becomes maximum at infinite dilution, that is del naught. The results obtained for weak electrolyte, namely acetic acid, and for strong electrolyte, namely KCl, are given in table 3. It is clear that the acetic acid, the value of Kd remains constant for dilute solutions, where for KCl the value of Kd falls rapidly with dilution. Application of Ostwald's dilution law. Ostwald's dilution law is applicable only to weak electrolytes. It is used in calculating the dissociation constants of weak acid and weak bases by determining the degree of dissociation from conductance measurements at given concentration C. Using the calculated value of Kd for a weak acid or a weak base which is constant at particular temperature, the degree of dissociation of that weak electrolyte can be determined at any concentration. Limitation of Arrhenius theory. Although Arrhenius theory could successfully explain the behavior of weak electrolytes, yet it could not explain various observed facts about strong electrolytes. Some of the important limitations of this theory are as follows. According to Arrhenius theory, ionization of the electrolytes takes place in aqueous solution. However, Briggs in 1912 through X-ray diffraction studied showed that many electrolytes are ionized even in their crystalline state. Example: Na positive, Cl negative. Strong electrolytes conduct electricity even in the molten state, so the ionization of the electrolyte takes place even in the absence of water. Thus, the Arrhenius theory could not explain the role of water in dissociation of electrolyte. Ostwald's dilution law, which is based on Arrhenius theory, fails for strong electrolytes. There is a good agreement between the degree of ionization calculated from the conductivity measurement and the one calculated from measurement of colligative property only for univalent electrolytes like NaCl etc. But marked disagreement in the values of alpha was found for bivalent electrolytes such as CuSO4, HgSO4 etc. Arrhenius theory proposes that equivalent conductance of electrolytes increase with dilution, thus increase in case of weak electrolytes is because on dilution more of the undissociated molecule of weak electrolyte dissociate. In case of strong electrolytes like NaCl are fully dissociated even in solid state, the increase of equivalent conductance with dilution could not be explained. It could not explain the variation of transport number with concentration. Debye-Heckel theory of strong electrolytes. In case of weak electrolytes, the increase in equivalent conductance with dilution can be easily explained on the basis of Arrhenius theory, according to which the conductance increases due to the increase in dissociation of the weak electrolyte with dilution. But this explanation cannot be applied to strong electrolytes as they are almost completely dissociated even at moderate concentration. In fact, the conductance of an electrolyte solution depends upon two factors. First is number of ions in the solution and second is speed of ions or the ionic mobility. In case of weak electrolytes, the increase in conductance on dilution is attributed to increase in the number of ions due to increase in the dissociation of the electrolytes. A quantitative explanation on the behavior of dilute solution of strong electrolytes was put forth by Debye-Heckel in 1923. Their theory is based on the idea that at a high concentration the ions are close together because the electrical attraction among the oppositely charged ions, each ion in solution surrounded by a large number of oppositely charged ions, which constitute an ionic atmosphere of opposite charge and hence affects the speed of the ion. The electrostatic attractions among the oppositely charged ions, which affect the speed of an ion in an electric field, are known as interionic effects. The two types of interionic effect are described as follow. Asymmetry or relaxation effect. Consider a central positive ion. This is surrounded by an ionic atmosphere of negatively charged ion. This ionic atmosphere is symmetrical in the absence of electrical field. When an electric field is applied, the positive ions moves towards cathode and negative ionic atmosphere moves toward anode. This leaves a large number of negative ions behind then in front of positive ion, and then the symmetry of the atmosphere about the central positive ion is destroyed. The excess negative ions left behind drag the positive ion backwards, and this slows down its motion in the forward direction. This effect arises due to asymmetry of ionic atmosphere of an ion and hence is known as asymmetry effect. It can be explained in another way by considering that the positive ions which leaves the ionic atmosphere of negative ions behind has to rebuild a new ionic atmosphere around it. However, the process of building up and dying away of ionic atmosphere is not instantaneous. The formation of new ionic atmosphere does not take place at the same rate at which the old ionic atmosphere dies out. Each of these processes takes some time, which is called the time of relaxation. During the time of relaxation, the old ionic atmosphere drags the moving ion backward and thus retards the motion of the ion. For this reason, asymmetry effect is also known as relaxation effect. Moreover, the central ion moves into an atmosphere where there is an excess of ions of its own charge, and this is also has a retarding effect on the movement of ion. Electrophoretic effect. In solutions, the ions are present in the solvated form. Each ion in the ionic atmosphere is associated with some molecules of solvent. Under the influence of electric field, the central ion moves in one direction and its oppositely charged ionic atmosphere along with the associated solvent molecules moves in the opposite direction. Thus the ionic atmosphere with its solvent molecules causes a retarding effect on the movement of central ion. The retarding effect is called electrophoretic effect. Besides these two effects, another retarding force is the frictional resistance offered by the medium due to the viscosity of the solvent and the dielectric constant of the solvent. This frictional resistance increases with increase in the viscosity of dielectric constant of the solvent. Both the factors, that is asymmetry effect and electrophoretic effect, are present in the solution of strong electrolytes and reduce the velocity of ions in solution. Hence, the value of equivalent conductance is lower than the value of at infinite dilution. Debye-Huckel-Onsager equation for strong electrolytes. Del C equals to del naught minus bracket 82.4 divided by eta into dt power half plus 8.20 multiply 10 raised to power 5 divided by dt by 3 by 2 into del naught bracket of close into root c, where del C equal to equivalent conductance of electrolyte at concentration, del naught equivalent conductance of electrolyte at infinite dilution, D is dielectric constant of the solution, eta is the coefficient of viscosity of the solution solvent, T is the temperature, C is the concentration of solution. Since the dielectric constant D and the coefficient of viscosity eta are constant for a particular solvent, thus at constant temperature T, the equation 1 can be written as where A and B are the constant for a given solvent and temperature. The constants A and B involves root dt in the denominator. Thus, when D and T increases, the interionic attraction would decrease. Thus, decrease in equivalent conductance will be less when dielectric constant or temperature is high. The first term A into root C is the measure of decrease of equivalent conductance due to electrophoretic effect. The constant A in this term involves eta, the viscosity of solvent in the denominator, showing that in a more viscous solvent, the decrease in equivalent conductance will be less because the speed of both the ions and the ionic atmosphere is slowed down in a more viscous solvent. The second term B del naught root C in the equation gives the decrease of equivalent conductance due to asymmetry effect. Verification of Onsager's equation. The Onsager equation can be verified by following tests. First is a plot of del C versus root C should be straight line. The slope of line should be equal to A plus B del naught. The graph of equivalent conductance del C for some univalent electrolytes in the aqueous solution at room temperature are shown in figure 9. Significance of Debye-Huckel theory. This theory has been used to explain the conductance behavior of strong electrolytes. Debye-Huckel theory successfully explained why the equivalent conductance of strong electrolyte at any concentration del C is less than the limiting value of conductance at infinite dilution, in spite of the fact that strong electrolytes are completely ionized. We know that the electrolytes dissociate in solution to produce cation and anions. Migrations of ions and transference number or transport number. First is migration of ions. When the current is passed the solution of an electrolyte, the ions migrate to the opposite electrodes. Thus, in the solution of AgNO3, the cations Ag positive ions move towards the cathode while the anions NO3 negative ion moves towards the anode. The movement of ion toward oppositely charged electrode is called migration of ions. The migration of ion through the electrolytic solution can be demonstrated by the following experiment. Take a U-tape made of a hard glass. The lower part of the U-tube is filled with 5% aqueous solution of agar-agar and small amount of copper dichromate. Since the salt is not available as such, it is obtained by mixing equimolar proportion of copper sulfate and potassium dichromate. It is green in the color and is allowed to set into jelly in agar-agar on cooling. The surface of the green jelly is marked by placing a small amount of powdered charcoal over the charcoal layer in both the limbs. A layer of KNO3 solution in agar-agar is placed. This layer also sets into jelly on cooling. Finally, an aqueous solution of KNO3 is added in two limbs and platinum electrode are inserted in it. When electric current is passed, the CO2 positive ions move towards the negatively charged electrode and their migration is indicated by the rise in blue color into jelly under this electrode. The orange colored Cr2O72 negative ions move up towards anode in the other arm of the tube. By comparing the movement of these colored bands in the two limbs, the velocities of the two ions can be compared. Velocity of ions and amounts liberated at electrodes heterospherical device. In accordance with Faraday's second law of electrolysis, which states that when same quantity of electricity is passed through solution of different electrolytes, the ions are always liberated in equivalent amounts. But the speed of cations moving towards cathode and the anions moving towards the anode are not necessarily the same. After experimental studies, Heathrow made following observation. The speed of cation moving away from an anode directly proportional to the fall in concentration of cations around the anode and the speed of anion moving away from cathode directly proportional to the fall in concentration of anions around the cathode. Hitrovs gave a general rule known as Hitrovs rule, which is stated as the fall of concentration around an electron is proportional to the speed of ions moving away from it. Hitrovs rule is illustrated by Hitrovs theoretical device shown in figure 11 as follows. Consider a shell containing an electrolyte solution. It is provided with an anode A and a cathode C. Dotted lines AA dash and BB dash are the imaginary planes which divide the cell into three compartments. The positive signs represent a cation while negative signs represent an anion. Before electrolysis, let there be 13 pairs of ions in the cell. The number of ion pairs in the middle compartment is 5 while there are 4 ion pairs in the two outer compartments. Now the following different causes may be considered. The condition of the system at the beginning of electrolysis is shown in figure 11 as 1. Case 1. When only anions move. Suppose that anions only are able to move under the influence of applied potential. When two anions move from cathodic compartment and enter anodic compartment, situation second is obtained. Although cations have not moved at all yet, the number of discharged anions and cations are the same. It is seen that the concentration in anodic compartment has not charged, while in the cathodic compartment the concentration has fallen by 2 molecules. Case second, when the anion and cations move at the same rate. Case third, when the cations move at twice the speed of the anions. From the above discussion, following results are obtained. First is the ions are always discharged in equivalent amounts on the opposite electrode irrespective of the speed of the ion. Second is the loss in concentration around an electrode is proportional to the speed of ion moving away from it. This is Hitrov's rule. We can now write fall in concentration around anode divided by fall in concentration around cathode equals to speed of cation divided by speed of ion, where U positive and U negative is the speed of cation and anion respectively. In writing the above expression, it is assumed that the liberated ions do not react with the material of the electrodes. In many cases, the discharged ion react with the electrodes, causing an increase in concentration around the electrode rather than the fall in concentration. One such case is discussed ahead. Case number 4, when the electrodes are attacked by the discharged ions. Then fall in concentration of in the anodic compartment due to migration of Ag positive ions equal to x minus y gram equivalents. It is clear from figure 12 that fall in concentration in cathodic compartment equals to increase in concentration in the anodic compartment equals to y gram equivalents. The ratio of speed of ions in the given as speed of Ag positive divided by speed of NO3 negatives equals to x minus y divided by y, transference number or transport number. During the passage of electric current through an electrolyte, the ions migrate towards electrode. Thus, the current is carried by the anions and the cations. The current carried by an ion is directly proportional to the speed of the ion. The higher the speed of ion, the more the current it carries, and hence greater its transport number. The fraction of the total current carried by an anion is called transport number or Hitrov's number. If UC represents the speed of the cation and UA that of the anion, then the current carried by the cation directly proportional to UA equals to KUA. The current carried by anion directly proportional to UA equals to KUA. Total amount of current equals to KUC plus KUA equals to K bracket into UC plus UA. Transport number of cation NC equals to KUC divided by K into UC plus UA. T of C equals to UC divided by UC plus UA. Transport number of anion N of A equals to KUA divided by K into UC plus UA. T of A equals to U of A divided by U of C plus U of A. Dividing equation 3rd by equation 4th, we get TC divided by TA equals to UC divided by UA. By adding equation 3rd and 4th, we get TC plus TA equals to 1. That is the sum of transport number of cation and anion of electrolyte is always unity. Hence, the whole of current is carried by the ions. Let the speed ratio of the ions UC divided by UA be denoted by R. The transport number of cation can be written in the term of R as follow. T of C equals to R divided by 1 plus R. Similarly, T of A equals to 1 by 1 plus R. Determination of transport number. There are two methods of determination of the transport of an ion. First is Hitrov's method. Second is moving boundary method. Hitrov's method. Principle. This method is based on Hitrov's rule. According to this rule, the fall in concentration around an electrode is proportional to the speed of the ion moving away from that electrode. Fall in concentration around cathode divided by fall in concentration around anode equals to speed of anion divided by speed of cation, or 1 plus fall in concentration around cathode divided by fall in concentration around anode equals to 1 plus speed of anion divided by speed of cation. Then total fall in concentration around both electrodes divided by fall in concentration around anode equals to U of A plus U of C divided by U of C. Inverting both the sides, we can write fall in concentration around anode divided by total fall in concentration around both electrodes equals to T of C. Expressing the concentration in terms of gram equivalents, we can write Tc equals to number of gram equivalent lost around anodic compartment divided by number of gram equivalents lost around both the compartments. The number of gram equivalents lost from both the electrodes equal to number of gram equivalents deposit or discharge as each electrode. This can be measured by placing a silver or a copper coulometer in a series. According to Faraday's second law, when the same quantity of electricity flows through the silver or copper coulometer, the same number of gram equivalents of Ag or Cu will be deposited. Thus, knowing the value of Tc, the value of Ta can be found as T of A equals to 1 minus Tc. From these equations, we can calculate transport number and hence the relative ionic mobilities from measurement of fall in concentration during electrolysis. It should be noted that above calculations are applicable only if the electrodes are not attackable. If the electrodes are attackable, then the transport number is calculated in different way, discussed a little later in this chapter. Measurement of transport number by Hitrov's method. For the measurement of transport number, the apparatus should be such that first there should be 3 separate compartments, that is anodic, cathodic and middle compartment. During electrolysis, there should be no intermixing of solution of these compartments. The solution from any compartment can be withdrawn without disturbing the solutions in other compartments. This is achieved by using a suitable apparatus in which the anode and cathode compartments are separated by a middle compartment as shown in figure 13. It consists of 2 vertical glass tubes joined together through a U-tube in the middle. All the 3 tubes are provided with stopcocks at the bottom. By closing these stopcocks, the mixing of solution in the cathode and anode limbs can be stopped. The cathode and anode is made of platinum. The cathode and anode may be made of Ag or Cu. If the transport number of Ag positive or Cu2 positive ions is to be determined, a silver or copper voltmeter is placed in series with the solution so that the same quantity of electric current passes through them. Procedure. First, the apparatus is filled with electrolytic solution of the ions whose transport number is to be determined. Second is that the electrodes are inserted and the cell is connected in series with a silver or a copper coulometer. The concentration of the electrolyte is found by titrating the solution with a suitable reagent. Fourth, the steady current of 0.01 to 0.02 ampere is passed for 2 to 3 hours so as to produce appreciable change in concentration. After electrolysis, the stopcocks of the U-tube are closed. The whole liquid in the anode compartment is carefully drained into a weighed flask and its weight is determined. It is titrated to determine the weight of electrolyte present. Seventh is the weight of silver deposited in the silver coulometer is determined. Eighth is there should be no change in the concentration of solution in U-tube. If the above experiment is performed using silver electrodes, in the case of nitrate ions take the silver anode, consequently there is an increase in concentration of Ag positive ions rather than decrease. The same experiment can be performed by using platinum electrode to avoid the attack of ions on the anode. Calculation. Case 1. When the electrodes are non-attackable. After passing electric current, let the weight of anodic solution taken W1 gram, weight of AgNO3 found to be present in it W2 gram, weight of water W1 minus W2 gram, W1 minus W2 gram of water contains W2 gram of AgNO3 after electrolysis, or W1 minus W2 gram of water contains W2 divided by 170 gram equivalents of AgNO3 equals to W2 divided by 170 gram equivalent of Ag equals to X. Say, before passing electric current, let W3 of solution contain AgNO3 equals to W4 gram. Weight of water in the solution equals to W3 minus W4 gram. Hence, before electrolysis, W3 minus W4 gram of water contains AgNO3 equals to W4 gram. The weight of water remains unchanged after electrolysis. W1 minus W2 gram of water will contains W4 divided by W3 minus W4 multiply W1 minus W2 gram of AgNO3. W4 divided by W1 W3 minus W4 multiply W1 minus W2 divided by 170 gram equivalent of AgNO3 equals to W4 divided by W3 minus W4 multiply W1 minus W2 divided by 170 gram equivalent of Ag equals to Y gram equivalent of Ag. When electrodes are non-attackable, the amount of Ag or Cu deposit in the coulometer is less than the actual increase in concentration of Ag positive in the anodic compartment. So Y is greater than X. Fall in concentration in anodic compartment equal to Y minus X gram equivalent of Ag. Let the weight of H deposit in the silver coulometer equals to W gram equals to W by 108 gram equivalent of Ag equals to Z eqvt of Ag. Then transport number of Ag positive equal to falling concentration around anode in G equivalent amount divided by amount of Ag deposit in voltmeter in gram equivalent equals to Y minus X divided by Z. Transport number of NO3 negative equals to 1 minus T of Ag positive. Case second, when electrodes are attackable, Ag electrode are used. In the case of their increase in concentration around the anode because every NO3 negative region the anode dissolves on Ag positive ion to form AgNO3. Thus, X is greater than Y. The increase in concentration around the anode equals to X minus Y gram equivalent of Ag. Thus, increase in concentration of Ag positive ion around the anode takes place even when Ag positive ions migrate from anodic compartment. If number of Ag positive ions had migrated from the anode, the increase in concentration of Ag positive ions would have been equal to Z gram equivalents. Fall in concentration around anode due to migration of Ag positive ions equal to Z minus into X minus Y gram equivalents of Ag. Hence, transport number of Ag positive ion equal to Z minus X minus Y divided by Z. Transport number of NO3 negative equals to 1 minus T of Ag positive. When copper coulometer is used in the experiment, the number of gram equivalents of copper deposited in the coulometer is obtained by dividing the weight of copper deposited by the equivalent mass of copper, that is 31.75. Moving boundary method. Principle. In this method, the migration of ions under the influence of applied potential is observed, and the speed of cations and the anions are determined. Then the transport number of cations and anions are calculated using the following relationships, where U of C and U of A are the speed of cation and the anion respectively. Apparatus. The apparatus used in shown in figure 14. It consists of a long vertical tube mounted vertically and fitted with platinum electrode at both the ends. To determine the transport number of the ions of an electrolyte M of A, two other electrolytes M-A and M-A each having an ion common with the experimental solute Ma are selected. The electrolyte solution M-A and Ma act as indicator electrolytes, while Ma acts as principal electrolyte. The solution of Ma is placed between the indicator solution to form sharp boundaries at A and B. As shown in figure 14, the anode is inserted in the solution of M-A and the cathode in solution of Ma-. For example, if Ma is KCl, then M-A can be LiCl and Ma- can be CH3COOK. The solutions are placed in the order of increasing density downwards to avoid mixing. The original boundaries are shown as A and B. In case of colorless solution, the boundaries can be seen because of the differences their refractive indices. To maintain sharp boundaries, the speed of indicator into ion M dash must be do not overtake M. Ions at A and A dash ions do not overtake A ion at boundary B, and sharp boundaries at A and B are mentioned. On passing electric current, the boundary A moves to A dash while boundary B moves to B dash. Thus, the speed of cation directly proportional to the distance A dash, the speed of anion directly proportional to the speed A B B dash. The transport number can be calculated as T of C equals to A dash divided by A dash plus B dash, and T of A equals to B dash divided by A dash plus B dash. Factors affecting transport number. We know that the transport number of an ion is directly proportional to the speed of the ion. The speed of ion in turn depends upon various factors described below. First is nature of the ion. In general, the smaller the size of ion, greater will be its speed. Hence, the transport number of smaller ion will be higher. Example, the transport number of H positive is greater in that of Na positive or K positive ion. Second is the nature of the other ions present in the solution. It may be noted out that the transport number of an ion does not depend upon the mobility of the ion alone. It is also depends upon the mobility of the other ion with which it is associated according to the equations. It follows that the transport number of cation depends upon the transport number of anion and vice versa. For example, the transport number of Cl negative is found to be less than in HCl than in NaCl. This is due to the fact that the size of H positive ion are much smaller than the N positive ions. Therefore, the speed of H positive ions is much greater than the speed of Na positive ions. Or therefore, the denominator terms in equation 1 is bigger than that in equation 2. Thus, the transport number of Cl negative in HCl is less than that of NaCl. Third is degree of hydration of ions. We know that the ions in solutions are hydrated. Smaller ions have strong electrostatic field and are heavily hydrated, and the large ions, because of weaker electrostatic field around them, are less hydrated. The speed of an ion is largely affected by the extent of hydration of the ion. As a result, the transport number of the ion is also affected. For example, Li positive ion is smaller in size than Na positive and is expected to have larger speed and thus higher transport number than that of Na positive. But actually it is reverse. That is, the transport number of Na positive is higher than that of Li positive ion. This is because the smaller Li positive ion is much more hydrated than Na positive ion. Similarly, the transport number of K positive ion is greater than that of Na positive ion because of more hydration of Na positive ion as compared to hydration of K positive ion. Next is temperature. It is observed that the ions tend to reach a transport number 0.5 as the temperature is increased. If the transport number of an ion is greater than 0.5, there is a decrease in transport number as the temperature is raised. While in case of ions having transport number less than 0.5, there is an increase in transport number with increase in temperature. For the ions having transport number around 0.5, there is very small change in transport number with increase in temperature. It is thus clear that in general the transport number of ion tends to approach 0.5 as the temperature is raised. Concentration. It is observed that the change in transport number of an ion with change in concentration is very small, but in some cases the increase in concentration results in formation of complex. In such cases there is notable change in transport number. For example, when concentration of CdI2 solution is increased from 0.005 m to 0.025 m, the transport number of Cd2 positive ions falls from 0.444 to 0.003. At higher concentration, the transport number becomes 0 and even attains a negative value. This is explained as follows. At higher concentration, there is formation of complex CdI for two negative ions as follows. At low concentration, only few CdI for two negative are formed. So Cd2 positive ions show their normal transport number, but the concentration is increased, more CdI for two negative ions are formed. The CdI for two negative ions migrate to anodic compartment at particular concentration. The number of CdI for two negative ions moving towards anode is same as the number of Cd2 positive ions moving from anodic compartment. As a result, there is no change in the concentration of Cd2 positive ions in anodic compartment. and the transport number of CD2 positive ions appears to have zero value. Next is intra-ionic effect. The ionic mobility and hence the transport numbers are greatly affected by the intra-ionic effects, namely relaxation effect and electrophoretic effects. These have been described in section 1.15. Coulomb's law. Coulombs studied the molar conductance at infinite dilution del m naught for strong electrolytes. He found an interesting pattern between the values of del m naught for different strong electrolytes. It was observed that the difference of del m naught of different pairs of strong electrolytes having a common cation or a common anion was almost same. Consider the following table for. It is observed that difference between the molar conductance K positive and Na positive is 23.4 ohm inverse centimeter square mole inverse irrespective of the anion. Similarly, the difference between the molar conductivities of Cl negative and NO3 negative ions is 4.9 ohm inverse centimeter square mole inverse irrespective of the cation associated with them. Thus, it may be concluded that each ions make a definite definite contribution to the molar conductivity at infinite dilution, irrespective of other ions. The individual contribution of the ions towards total number of conductivity of electrolyte is called molar ionic conductivity. As a result of these observations, Coulombs gave a generalization called the Coulombs law. It states that at infinite dilution, where the dissociation of the electrolytes is complete, the molar conductivity of the electrolyte is the sum of limiting ionic conductivities of the cations and anions, each multiplied by the number of ions composing one formula unit of electrolyte. Coulombs law for an electrolyte AXPY may be mathematically stated as where x and y represent the number of positive negative ions furnished by one formula unit of the electrolyte. Del m naught AXBY is the limiting molar conductance of the electrolyte AXBY, and lambda naught into A positive and lambda p naught for B negative are the limiting molar conductivities of the cation A positive and anion B negative respectively. For example, NaCl del m naught for NaCl equals to lambda naught Na positive plus lambda naught Cl negative. Illustration. Based on Coulomb's law, it is possible to calculate the molar conductivity of a weak electrolyte at infinite dilution by simply adding and subtracting the del naught values of given electrolytes. For example, for acetic acid we have. In terms of equivalent conductance, Coulomb's law may be stated as the equivalent conductance of an electrolyte at infinite dilution is equal to the sum of the equivalent conductance of cation and anion, where del naught positive is the ionic conductance of cation and del naught is the ionic conductance of anion at infinite dilution. This is in accordance with Coulomb's law. This equivalent conductance del EQ and molar conductance del M as related as where x and y are the number of cation and anion respectively present in one formula unit of the electrolyte, and Z positive and Z negative are the charges of cation and anion respectively. Coulomb's law is called law of independent migration of ion because at infinite dilution all electrolytes are completely dissociated and all intra-ionic effects disappear. In such conditions, each ions migrated to the electrode independent of the nature of the co-ion and makes a definite contribution towards the molar conductivity of electrolyte, which depends only on its own nature, not at all on the ion with it is associated. Ionic mobility. The ionic mobility of an ion is the speed of the ion in an electrical field of unit strength. It may be defined as the distance traveled by an ion per unit time when a potential gradient of 1 volt per unit distance is applied, it is represented as U. Mathematically, ionic mobility speed of the ion divided by potential gradient applied. Its unit is centimeter square second inverse and V inverse. When the speed of ion is taken in meter per second, then the ionic mobility is expressed as meter square second inverse V inverse. Table 5 shows the ionic mobilities of same selected ions at infinite dilution in aqueous solution at 298 Kelvin. It is clear from table 2 that H positive ions and O negative ions possess abnormally high ionic mobilities. It may be mentioned that ionic mobilities depends on concentration and temperature. An increase in temperature increases the mobility of all ions, the temperature coefficient being almost the same for all ions in a given solvent. It has been observed that ionic mobilities increased by about 2% per degree rise in temperature near 298 Kelvin. Relationship between equivalent ionic conductance and ionic mobility. Ionic mobility and equivalent ionic conductance are related as ionic mobility equals to equivalent ionic conductance divided by 96500, where U naught and lambda I naught are the limiting values of ionic mobility and equivalent ionic conductance respectively. The relationship is derived as follow. Consider an electrolyte S. So consider an electrolyte solution contained in 1 centimeter cube. The conductance of this solution is specific conductance. Now when a potential difference of 1 volt is applied between the electrodes, then electric current flows through solution equals to 1 by R equals to conductance. In this case, the conductance of solution is equal to its specific conductance. Suppose the concentration of solution is C gram equivalents per liter. Further, assume that C is very small and the electrolyte is completely ionized. Then, limiting equivalent conductance del naught equals to specific conductance divided by C. K equals to C del naught, but del naught equals to lambda C naught plus lambda A naught. So K equals to C into lambda C naught plus lambda A naught, where lambda C naught and lambda A naught are the equivalent ionic conductances of cation and anide at infinite dilution. Comparing equation 1 and 3, we can write current flowing through electrolyte solution equals to C into lambda C naught plus lambda A naught. Let UC naught and UA naught be the absolute velocities of cation and anion at infinite dilution. Since the potential gradient is 1 volt per centimeter, therefore the cations at distance UC naught centimeter from the cathode will get liberated at cathode in 1 second. Similarly, the anions at distance UA naught centimeter from the anode will move towards anode in 1 second. The solution contains C gram equivalent of electrolyte. The cations liberated at cathode in 1 second equals to CuC naught gram equivalents, and the anions liberated at anode in 1 second equals to Cu naught G equivalents. According to Faraday's law, 1 gram equivalent of an ion is discharged when 96500 coulombs, that is 1 Farad of electricity, is passed through the solution. For discharging C into UC naught plus UA naught gram equivalents of cations, the current flowing the solution equals to 96500 multiply C into UC naught plus UA naught coulombs. Comparing equation 4 and 5, we can write UC naught equals to lambda C naught divided by 96,500 and UA naught equals to lambda A naught divided by 96,500. Relation between ionic conductance and transport number and equivalent conductance of ions. By combining the Coulomb's law with the transport number measurements, we can calculate the molar ionic conductance at infinite dilution. By combining the transport number of cations in terms of ionic mobility is given by TC naught equals to UC naught divided by UC naught plus UA naught. Transport number of anion is given by TA naught equals to U of A naught divided by UC naught plus U of A naught, where TC naught and T of A naught are the transport number of cations and anions respectively, and UC naught and U of A naught are the ionic mobility of cation and anion respectively. At infinite dilution, the equivalent ionic conductance of an ion is proportional to the ionic mobility at infinite dilution. Lambda naught directly proportional to U naught. Equation 1 can be written as T of C naught equals to lambda C naught divided by lambda C naught plus lambda A naught. But from Coulomb's law, the equivalent conductance at infinite dilution for an electrolyte is given as del naught equal to lambda C naught plus lambda of A naught. Equation 3 becomes T of C naught plus T of A naught equals to 1. T of C naught equals to 1 minus T of A. Thus, equation 4 can be written as lambda C naught equals to del naught into 1 minus T of A naught. Similarly, for an anion, we can written as lambda A naught equals to T of A naught multiplied del naught. Equation 6 can also be expressed as lambda A naught equals to del naught multiply 1 minus Tc naught. Thus, the molar ionic conductance of an ion can be calculated by multiplying the equivalent conductance at infinite dilution of an electrolyte containing that ion by its transport number. Effect of temperature and pressure on the molar ionic conductance. The molar ionic conductance is found to increase with increase in temperature. From equation 6, it is clear that the molar ionic conductance is inversely proportional to the coefficient of viscosity eta of the solvent. Thus, the viscosity of the solvent decreases with increase in temperature. Thus, molar ionic conductance of an ion lambda plus minus increases as the temperature increases. For example, for ions other than H positive and OH negative, the increase in ionic conductance is about 2%. For 1 degree rise in temperature in the temperature range of 0 to 100 degrees Celsius, whereas for H positive and OH negative ions, the increase in ionic conductance is about 14% and 16% respectively per degree rise in temperature. Molar ionic conductance decreases and increasing pressure. This is because the viscosity of the medium increases and increase of pressure. Application of conductance measurements. Applications of Coulomb's law. The conductance measurements have many applications in theoretical as well as analytical chemistry. Some of the applications are discussed as follow. Degree of dissociation of weak electrolyte. Arrhenius theory assumes that in case of weak electrolytes, the increase in equivalent conductance on dilution is due to increase in the degree of dissociation of the electrolyte. It is evident that when limiting value of equivalent conductance is approached, the degree of dissociation is unity. Thus, the degree of dissociation alpha is given by alpha equals to del C divided by del naught, where del of C is the equivalent conductance at any concentration and del naught is the equivalent conductance at infinite dilution. It may be noted that above relationship holds only for weak electrolytes. The value of del naught for strong electrolytes can be calculated using Coulomb's law. Dissociation constant K of A for weak acids. Consider the dissociation of a weak acid HA having initial concentration Hc moles per liter. Let alpha be its degree of dissociation. Then we can write, applying the law of chemical equilibrium, the dissociation constant K of A of weak acid H of A can be written as K of A equals to C alpha square divided by 1 minus alpha. The value of alpha can be calculated from equivalent conductance. Alpha equal to del C divided by del naught. Substituting the value of alpha in expression 1, the dissociation constant K of A for weak acid can be calculated. Third is solubility of sparingly soluble salts. Salts such as AgCl, PbSO4, BSO4, etc. dissolves to a very small extent in water, therefore are called sparingly soluble salts. Since they are very slightly soluble, their solutions may be taken at infinite dilute. Moreover, because their solutions are saturated, their concentration may be taken equal to their solubility. Thus, by determining the specific conductance and equivalent conductance of such solution, we can easily calculate its solubility as, let S be the solubility of the sparingly soluble salt in gram equivalent per liter. Then the volume of solution in CC containing 1 gram equivalent of salt will be 1000 divided by S. Equivalent conductance del and specific conductance kappa of such solution are related as del equals to kappa multiply 1000 multiply S. As the salt is strongly soluble, its solution may be taken as infinite dilute. So del may be taken as equal to del naught. Thus we can write del naught equals to kappa multiply 1000 multiply S, or S equal to kappa multiply 1000 multiply del naught. Del naught can be found by applying Coulthard's law to calculate solubility in grams per liter. The quantity S is multiplied with equivalent mass of the salt.